Rick, is my audio on?
Yes, it
Yeah,
is.
Jim, I can hear you.
You're good.
Okay. All right. So we had, Rick reported that we had a power outage, at least on the east side of Manhattan Beach this morning. So it came back on about 10 minutes ago, I guess, 10, 15 minutes ago. So that may or may not have an impact upon our attendance. Just a disclaimer here. This presentation by Rick Hefner about JPL, about the Perseverance rover that landed on Mars a week or two ago. The announcement, the disclosure is that I worked at for JPL in engineering for back many years ago, back in the 1960s. So I had not good knowledge of what was going on then. I have no knowledge now.
Better get a place.
So-
Oh, I think he might be walking. I'm gonna need some salt.
So Rick, you're ready.
Hey, great. Thank you, Jim. Hey, let's see. This was fun putting together, and I'm happy to share, recognize, just being involved in the space business for me is kind of a dream come true. I grew up as a little kid in the Midwest. I tried to find my high school graduation picture. I think all copies of it have been burned. But if you saw it, it would have been clear to you at the time that I was destined to be a nerd of some sort. And growing up in Lafayette, Indiana, the home of Purdue University, for my family, that was the one university I could actually afford to go to. And it turned out to be an outstanding university for aerospace engineering. As a youngster going to school, I met people like Neil Armstrong and other astronauts. It was really just fascinating. I just couldn't imagine the joy of working a career in aerospace. And at the time, I was getting my bachelor's and master's degree from Purdue in aero engineering. The fantasy was that someday I would get to visit JPL. And maybe if I was lucky, they would let me go visit the Caltech campus. And so to grow up to have a 40-year career in aerospace, working for companies like Aerospace Corporation and TRW and Northrop Grumman, getting to work on a variety of really interesting aerospace systems, and at the culmination of my career here, getting to teach at Caltech and to work with the JPL people on a daily basis is just really fascinating. So I put together a little summary kind of about the Mars Perseverance rover, and hopefully give you a little bit of a exposure to what it's all about. So we'll start with a little video here.
To the ancient Romans, the planet Mars was symbolic of blood and war. But to many people today, the red planet may hold the key for a bright new future for humanity. The story of Mars began about 4.5 billion years ago when gas and dust swirled together to form the fourth planet from the Sun. Mars is the second smallest planet in the solar system, with a diameter just shy of the width of Africa. In fact, its entire surface area is similar to that of all of Earth's continents combined. Much like its terrestrial cousin, Mars is dense and has a rocky composition. At the center of the planet is a core made of iron, nickel, and sulfur, which may have created a protective magnetic field during Mars's earlier years. Enveloping the core is a rocky mantle made of silicate minerals and a crust rich in iron. These iron minerals react with the trace amounts of oxygen in Mars's atmosphere and rusts, giving the planet its signature reddish hue. While its blood-like appearance inspired the ancient Romans to name Mars after their god of war, The planet's rusty color could be considered symbolic of the planet's prime days long past. Today, Mars is dry, desolate, and cold, with temperatures dropping as low as -225 degrees Fahrenheit. But billions of years ago, the planet was much warmer, more geologically active, and had a watery surface. Lake beds and river valleys snake along the face of Mars, indicating that liquid water was, for a time, present. Volcanoes, such as Olympus Mons, the largest volcano in the solar system at 3 times the height of Mount Everest, once erupted lava. But by about 50 million years ago, soon after Earth's dinosaurs died out, Mars's volcanoes also went extinct. Water on the red planet still exists today, but mostly in the form of polar ice caps. Because of factors such as the presence of water, some scientists believe life may have existed on the red planet and may exist again. Since the 1960s, space programs from around the world have launched missions to Mars in attempts to understand the planet's past, present, and potential for sustaining life. Life on another planet may well be out of reach for the near future. But if any planet could give us hope, Mars may hold the key to the survival of humanity. After Earth's dinosaurs died out, Mars...
So a little bit of background on the folks that are exploring Mars. Probably everybody here is familiar with the Jet Propulsion Laboratory, or JPL. It was actually, the origins of JPL were actually back in the 1930s. And really it dates back to a group of students at Caltech who were interested in rockets, in rocket fuel, and they formed the Rocketry Club way back then. And they experimented with different formulas. At the time, the real goal was to try to come up with the most potent rocket fuel so that we could lift off big things. And they were having sort of limited success. And they ended up researching kind of who was doing work, and they ran into von Karman, leading researcher at the time, and wrote him letters and said, hey, we have these ideas about rocket fuel. What do you think? And at the time, von Karman kind of thought they were all kooks. So he didn't really want to write them back. But he eventually started looking at some of the notes and realized that they had some really good ideas, and eventually made contact with them, and eventually came to Caltech and worked with them in terms of rocketry. Now, at the time, the JPL Rocketry Club met and did all their work on the Caltech campus there right in the middle of the city of Pasadena. Let's see, and they kept firing off rockets and exploding rocket fuel in the middle of campus to see if they could make the biggest explosion. And eventually the city of Pasadena said to them, you know, maybe it would be a good idea if you guys didn't blow up stuff right in the middle of the city of Pasadena. You're making us kind of nervous. Why don't you go way up there in the Arroyo, up in the desert where nobody is, and blow your stuff up there. And so they did. They hiked up into the hills there. It's all scrub brush, nothing really they could damage up there. They started shooting rockets off. Eventually they decided they probably ought to have a bathroom or a porta potty there, a little shed to maybe keep some of their equipment so they didn't have to keep schlepping it up the hill. Eventually maybe put some power there to run some computers, etc. And it kind of kept blossoming from there. It became JPL at that point. It's interesting to know that JPL looks a little differently today. Today takes over 177 acres. There's about 6,000 people employed by JPL, and it's quite a leading researcher. Very interesting. some people say, well, why is it called JPL? Why is it Jet Propulsion? Why isn't it Rocketry Propulsion or Rocket Lab or something like that? And you have to remember at the time that JPL was being formed, rocketry was space science fiction stuff. It was the sort of things that, Buck Rogers did rockets. And JPL was trying to get some contracts with the Army to do work on this. And the Army said, we're not going to pay for looking at rockets. That's just craziness. That's just never going to happen. That's really science fiction. Now, we are interested in the rocket fuel, and as a way of propelling our jets, making them go faster, we could propel planes with some rocket assisting, we could take off on their short landings, etc. So if you want to study jet propulsion, then we might be interested in doing some funding. So, no rockets, jet propulsion, and the name Jet Propulsion Lab was built. So do we have anybody else here on the line who's worked up at JPL besides Jim?
Rick, could you say a thing about what was going on in Germany with rocket development?
A lot of the same thing. We had Werner von Braun, which I think the Rocketry Club also wrote to. Was doing Germans, the V2, etc. They were kind of ahead. Most people were thinking of rockets as weapons, right? Could we deliver ordnance? Could we boost planes at the time? And we had the same sort of thought too. It was only things like Sputnik that got people interested in rockets as a way to explore outer space. By the way, it's interesting, JPL was actually responsible for the first US object in space, which was Explorer 1. Explorer 1 was a small satellite like Sputnik. It was after Sputnik, so the Russians beat us to space. I think the one satisfaction we took really was just a communication device. You could communicate to it, could beat back to you. That's really pretty much all it could do. Explorer 1 was different in that it included a piece of equipment. It actually had a little Geiger counter inside there and could send back readings from the Geiger counter. And that's how we were able to confirm that the Van Allen belt was there.
So to answer your question, Rick, my son Roger works there.
Yeah, that's right. Roger does. Okay, so not the Rocket Propulsion Laboratory, but the Jet Propulsion Laboratory. JPL really has two kinds of missions, two kinds of systems that they develop. So the first kind is their planetary exploration, and really there's been over 100 missions launched exploring everything. And this is just a little timeline kind of dating from 1958 up to present. So you can see just lots and lots of different explorations, a number of programs that went back. Perhaps maybe the grandest one, the one that most people know is Voyager, right? I mean, it's even been in the Star Trek movies, right? Voyager was designed to, and put together to be kind of an all-planetary observer. And it actually flew by the four gas giants, the four big planets in our solar system: Jupiter, Saturn, Uranus, and Neptune. Voyager became the first man-made object to actually leave our solar system. It left a few years ago. And they're actually still in communication. Voyager is too weak, and its battery is too weak now because it's too far from the sun for the solar panels to get much energy. And so all they have right now from Voyager is what they call a heartbeat signal. So every once in a while, Voyager says, "I'm still here," and JPL says, "Great," but they're actually still communicating with it today. The way longer than the mission was designed to last here. You probably have heard other programs: Galileo, Hubble Space Telescope. So here's a picture of Voyager, right? Kind of all seen this, or V'ger, they call them the Star Trek movies, right? So still out there, still kicking way, way, way beyond Pluto, way beyond what we think of as our solar system. And here's one of the latest ones. This is the James Webb Space Telescope. Amazing program. Actually, this program is in the high bay that you're looking at right here over at Northrop Grumman in Redondo Beach. They're actually testing the James Webb Telescope. It's approaching launch here pretty soon. Things are a little iffy on schedule because of the COVID, but just a fascinating system. You're looking at some incredibly ground mirrors, and once they get the James Webb Telescope up, it's going to be many, many, many times more precise and accurate than any other telescope we've ever built to date. And it's going to just look at different frequency bands, look far into the universe, really just an amazing system. And you can actually go over when Northrop has their open house days, you can actually go over and see this in their huge high bay, which is about the size of about 10 gymnasiums put together. It is really, really impressive.
So Rick, that's in Redondo Beach, North Redondo, correct?
Yep. Mm-hmm. Yep. Right over there.
It's like a mile or two from here.
Absolutely. Absolutely.
Rick,
And it's the most amazing, technologically advanced thing that's ever been built in the world at this point. It's the #1 technology development. Yeah. I heard comment.
Rick, will you let us know when they have this open house? I'd like to see this.
Yeah, we will. What's fun is I get to work with classes on systems engineering, and Northrop is nice enough to let me and my classes come over and take a look at it in the high bay. And we actually get to talk to a lot of the engineers that worked on the Hubble and listen to their how they designed it, what they're thinking of it, what they're concerned about. It is a fascinating marvel and an incredibly complicated system.
Rick, one more question. This is being recorded, I believe, and the recording will be able to be played back when it's posted, which will be probably in 3 or 4 days.
Yeah. Mm-hmm. Good. Yeah. Yeah, we're recording. Good. Okay, so I mentioned JPL has two kinds of systems. One is the planetary missions. The other is Earth orbiting missions. And I think a lot of people don't know about this. JPL is very interested in sending satellites up that rotate around the Earth in various orbits in various ways and various types. Most of them are associated with some sort of Earth sciences. So we have satellites up there studying climate change, rain and snowfall patterns, the way oceans winds work and how that contributes to changes in our weather patterns, et cetera. Ocean temperatures turns out to be a big thing. And so we are gathering lots and lots of information up there. Landsat satellites you can see there are mapping all the land masses and changes in land masses and sea levels over time. So just a tremendous group of satellites. There's always several satellites up there at any given time. They're not flying this close. This is obviously just a artist's perception, but it's a huge part of the JPL mission, which doesn't get a whole lot of attention. Let's see. This is just a little picture of one of the recent rovers, kind of in the, this is Curiosity. This was, they're doing some assembly or some testing. You can see that the clean room. This is one of the rooms up at JPL, kind of their version of the high bay. You can see all the people with the masks on, et cetera, trying to keep down the any kind of particles. Obviously, when we sneeze, the little flecks of dead skin on our skin, et cetera, those get off and get into any of that sensitive electronic components. Everything gets completely ruined. We're going to talk more about some of the equipments on the rovers in just a minute, but I want you to take a look at it. And if you notice, right, on the rover, there's no JPL decals, right? Which seems really weird. I mean, they have pride in their work. You'd think they'd put a decal. Well, it actually turns out that there's a NASA rule that you're not allowed they don't like any of their individual centers like JPL to advertise themselves. That, you know, how you're part of NASA, you can put a NASA logo on if you want to, but you can't put a JPL logo on. And that was really frustrating to the JPL people who take a lot of pride in their work, obviously. So the trouble is, you know, you can't frustrate engineers for very long. We're too devious and ingenious. So look at the wheels. So these are wheels designed for the Martian surface. Martian surface, as you saw in the video, was, you know, very dusty, thick layer of dust and rock, and it's super cold, and so you can't have things like rubber or anything, obviously. So these are metal wheels, but you notice that they look kind of odd here, and obviously the design of the wheels is so that we don't get stuck in the dust. That would be bad. We've actually lost one of the rovers that way, just got stuck in a big sand trap. Notice also the weird kind of black axles on top of the wheels. This is called a rocker bogie system. Basically, it allows the wheels to all move independently. It turns out that's an easy way to get over rocks and stuff. But if I look at the composition of the wheels, this is something where the JPL engineers got around things. So they knew that in pictures of the rover, when you look back over the rover, you look back over where the rover had been on Mars, you'd see the dust and you'd see the tracks of the wheels. And so what they did was they designed the wheels with a built-in Morse code. And so if you look back over the tracks that the rovers leave on Mars, actually spells out JPL in Morse code over and over again. So, interesting way to get around the idea. Yeah, we can't put a logo in, but we can leave our JPL logo all over the surface of Mars. This will give you an idea of some of the history of the various rovers that we've had built by JPL on Mars. So we start with the little tiny gold one in the bottom left-hand corner here. This is called Sojourner. It landed on Mars in 1997. You can see it's pretty small. It's about the size of a TV tray, and it's really designed to communicate, to move around a little bit on Mars. And you can see that it's powered by that solar array there that's on the top of that. So they basically just drop that onto Mars, and it could run around. Not really much science, not really much explorative capability, but it proved that we could get to Mars back in the 90s. The one in the upper left is, there were a twin set of those, Spirit and Opportunity. And those were landed on Mars, originally Spirit, about 2004. And you can see it's a lot bigger. It's got a lot more equipment. It's got a little arm on there with a drill on it. They can drill things if they want to. And you can see that to power all that extra weight and size, they've got much more extensive solar panels. Now, the solar panels are the interesting parts of it, you know, powering the Spirit. The real question is, if I put something up on Mars, how long did it last? Okay, so as an example, the Spirit, the bigger one there on the left-hand side, was designed to last 90 Martian days, which is, a Martian day is slightly longer than an Earth day. So 90 days, not very long. Well, what limits the ability? Well, there's always risk. I can get stuck in the sand. The electronics can fail, right? But what really limited 90 days was these solar panels. So we mentioned before the Mars atmosphere, very thin, carbon dioxide based, lots and lots of dust. Just think of going in 2 inches of dust all the time. Let's see. The dust blowing around with the winds on the surface of Mars, the dust will start to accumulate on the solar panels. And eventually they just get dusty enough and there's nobody there to dust them, and there's really no practical way to design any kind of wiper or anything for them without damaging all the electronics there. And so eventually what they figured is after about 90 days, the solar panels would get so dusty that they wouldn't produce enough energy to power the rover to communicate. By the way, the little thing that looks like a little film canister, the little red canister off to the right, that's the communication antenna. So they figured eventually the panels would get dusty enough, and that's what would limit the life of the rover. We'd just power down. We wouldn't be able to power back up. We wouldn't be able to communicate. It would be dead on the surface of Mars. What's interesting is they found a different phenomenon they didn't expect. Was that's the way it started. Panels started accumulating dust, looked like it was going to die pretty quickly after 90 days. And then one night, a huge Martian storm blew through and actually blew a lot of the dust off the solar panels. And all of a sudden, the power output of the solar panels went way back up again. And then we slowly accumulated dust, and it turns out, several days later, another Martian storm went through and blew all the dust off again. And it turned out the storms were regular enough that we could actually continue blowing dust off the panels, and they actually lasted, instead of 90 days, the first Spirit actually lasted 2,200 days. So much farther than design life, which is why when we design things, we always design all the electronics and stuff to last for much longer, because we always know there's things we don't understand about the environment we're going to. And it actually didn't die because of the solar panels. It actually got stuck in sand, although the solar panels had got dusted enough that it was tough to generate enough power. If you look at the bigger, much bigger rover on the right, this is Curiosity. And each rover uses technology from the previous rover and kind of insights that they've developed. So there's some same things. Look at the same or similar rocker boogie system there with the axles to the wheels. Wheels are it's all-wheel drive. Of course, everything's moving independently. They changed the wheel design a little bit. Notice that it's the tread design is now kind of a zigzag, which they found was better for getting through sand than kind of the straight lines that they had on the others.
Rick, can I ask a question?
Adding other equipment. Yeah, go ahead, John.
How do you package that big one on the right? Does it fold up into a smaller package, or how do you get it in a rocket ship?
It folds up a little bit. So the big arm with the drill on the left-hand side there, that folds back and lays down against the top. And then the mast there with the camera, a little red eye on the top there, that folds down in.
Yeah, it's a little bigger screen.
And so it's interesting. It's actually one of the challenges, and we're going to see a video in a minute here. How do you get these things down on the surface, right? We don't usually have enough propellant once we get all the way to Mars to land things very slowly. So Curiosity was a little bit easier. Spirit Opportunity was kind of interesting. The one on the left there, it actually folds up, those arms and stuff fold up inside there, and then the panels fold up on top of them. And the way that they got Spirit and Opportunity down was they lowered it down on a rope, on what's called a bridle, and then they inflated airbags around it, cut the bridle, and let it bounce on the surface on top of the airbags until it landed. And once it quit bouncing around after 10 or 12 times, and it rolled around for a while, and then it stopped, inside that that Spirit and Opportunity was a pyramid which held it. And all they did was, when the pyramid stopped, they deflated the airbags. They looked to see what was the orientation of it. They had to put the pyramid onto one side so it was standing straight up. And then they unfolded the pyramid and they drove it off. You're going to see the way they landed unfold the Opportunity here in a little bit differently, because they couldn't use airbags because it's so much bigger. It's about the size, obviously, you can see it's about the SUV.
Hey, Rick,
Yeah.
can you let Phil into ADG? He's got a bigger computer than I do.
Okay, yeah, I just did.
Did they learn a lot of fold-up skills from the Rose Parade?
I'm not sure there was a lot of bleed over there, but maybe the Rose Parade may have learned from them here. But there's some pretty smart mechanical people, and a lot of thinking goes into how do we get out of this. You notice this is really kind of JPL, what JPL is known for. It's their signature in terms of engineering is they build a platform, and then lots of other labs and universities build gizmos go onto it. So JPL said, hey, listen, we'll get this this Jeep body with some wheels on it to Mars. Who wants to put something on our Jeep body? And so the people with that drill in the front end said, hey, we got this drill. We think that would be really cool. And the people with that camera mast said, hey, we have this cool camera that we want to point. And by the way, it's got a laser. You got everybody interested, right? All the other electronics you see there are different sensors, other lab equipment, et cetera. And so then basically the scientists all get together in a room and they look at all the different options that they have and they say, okay, we'll take that gizmo and that gizmo and that gizmo, and that's about all we have room for, and then we got it, right? So that's the way it works. Also, if you notice, Curiosity doesn't have any solar panels because much bigger system. They can't really count on using solar for that, and because of the expense of it, they don't really want something that's going to last for 90 days or something that they have to hope for Martian storms on. So Curiosity uses a nuclear power. So it's something called a radioisotope thermoelectric generator. So they take plutonium, and as the plutonium decays, it generates heat, and they have a device that converts that heat to electricity, and that produces enough power to power the rover. By the way, they only run the rovers during the Martian days. Martian nights, they don't. Back in the early rovers, they didn't run it at night because they needed power, and of course they wouldn't have any sun at night, so they couldn't run the panels. Even though there's little batteries on board that store it, they couldn't store enough. And then they don't run Curiosity at night because they're afraid they'll run into things that they don't see, or they'll run into a rock or something. And that's their biggest panic. If you're the rover driver, right, you don't want to run into a rock, get a wheel stuck, and then all of a sudden you can't use the rover anymore because you're stuck in a wheel. So everything is designed basically to keep the system as mobile as possible. Any other questions about the three things that came before Perseverance?
Well, you might have said it at the beginning, I'm not sure, but the difference in gravity, how much does like Curiosity weigh here and what does it weigh on Mars?
You know, I don't know the difference. It's less, John. It's not a lot less.
Oh, okay.
I don't know the difference of that. I know the engineering stuff. I don't know much of the science stuff.
What's the lifespan of the Curiosity then?
So Curiosity was designed for I think a couple 3 years.
Wow.
And it's actually been up, it's actually still running around up there now in 21. So it's actually at 9 years now. So it's that's kind of traditional. We try to over design these things. We design it to last longer because there's always sort of one killer thing and you never would know what it is, but you want all the rest of the systems to work as long as possible. So.
And is JPL then the one driving it now?
Yeah. So there's an operational group at JPL. If you've ever NASA Houston, right? We see the people sitting at long tables staring at screens. I used to have that job for the Air Force. That was a fun job to do. And there's a similar room at NASA called the Control Center, and that's where they drive it from. And interestingly, because the NASA day is different than an Earth day, the day works forward relative to the Earth day. So if you're the driver of the rover and you're coming to work at 8 a.m. NASA time, Martian time, it might be 8 a.m. Earth time, and then the next day 8 a.m. Martian time will be 8:10 Earth time, and the next day it'll be 8:20, and so eventually you're coming to work in the middle of the night, even though it's still Martian day.
So Rick, one more thing. So when you give a command to the rover, the transit time for your command to get to Mars and for the rover to respond, and then for you to see it back on Earth, that transit time, of course, it depends upon where they are in the orbits.
Yeah.
But typically so it varies with the position of Mars relative to Earth, which is constantly changing.
Typically about 14 minutes. So they command, so they're not driving in real time, right? And they don't have a camera someplace they can look at it. They can look from the cameras that are on the rover, kind of a sense of where the rover is. So what they do is they look with the cameras where they are, they decide they want to go, and they say to the rover, okay, move 10 feet forward and to the right a little bit. And they send that command, and it takes 7 minutes, gets up to the rover, and then the rover gets the command and it moves 10 feet and to the right a little bit, you know, and then the rover says, okay, I'm done. And they send a command back, and then 7 minutes later on Earth, we get a command that said, yep, we moved there. We're still good. We're still moving. We're still alive. Okay. And they say, all right, move over here. And so you just kind of inch up on things little by little. And 10 feet would be a long way to go. Probably you're more likely to go a couple of feet at a command. Let's see. The Tories said the mass is a third, so a third the gravity. So it's a good way to lose weight really quickly. Just go to Mars. Okay. So what are the missions of the rovers? Well, they're all very similar. They're trying to characterize the rocks and soil. So we want to know a little bit about the geological composition, how it got there, all kinds of things. The early rovers were looking for signs of water. And the reason why is, you know, ideally we'd like to know if life ever existed on Mars. We're pretty sure it doesn't exist today just because of it's such a hostile climate, right? 215 degrees below Fahrenheit. It's pretty unlikely that any kind of life would live in that. But was there water at some point? We see things that look like river deltas, like old river deltas and other things there you saw in the videos. So questions, can we find water? Is there water below the surface, below the dust that we can see, etc.? And then we want to verify data like the Mars Orbiter is a satellite that went up and orbits Mars. We tried to gather lots of data, especially about where we were going to land and make sure it was a reasonably safe period thing, etc. And so we want to kind of calibrate that data. So now we're down on the ground, we can actually measure it. So the satellite in orbit said this rock was this big. We get down, we can actually measure it more carefully. Did that make sense? Or the orbiter gathered some spectral data that said the composition is this, and we get down and we can actually do more. So it was designed to do that. You can see we've got a couple of cool gizmos to do that. We've got a drill there in the front. We're going to show a quick video on that in a second. And then we got this really cool camera with a laser. And so we can laser various rocks and then look at them to see what kind of emissions they're putting out to see what they might be doing. Right. By the way, if you look at the very back, the gray thing behind the camera looks kind of like has fins and kind of a little cylinder. That's the radioisotope. That's the plutonium's inside there putting off heat, and then they're generating electricity with a canister. Actually generates electricity to power everything. If you see something that has what looks like copper on it, that's actually gold, and that's probably a communication device of some sort, or it could be a very special sensor. Let me show you a little bit of some of the science involved. Now, this is the last generation. This is the Curiosity science. This is an artist's conception of the Curiosity. John, you were asking, this is the way it gets landed. It gets lowered down on a bridle and basically dropped like a helicopter would drop a package. So we can see sun come up, right? There's a good picture of the radioisotope there. That thing with little fan blades on it. Right? So now they're unfolding the mast with the mast cam on it. Right. That little device is both a camera and a laser. Right. So we can look around.
Incredible.
What's something interesting that we might look at? Where might we go over and get some data? And we're just exploring the thing. So we basically put it down. The reason why we want a rover is we want to drive around to some of this stuff. We couldn't land accurately enough way up on Mars to know where. Also, is there a big rock in front of me? Maybe I don't want to go that way because I'm going to get stuck. If it gets stuck up underneath the rover, then like your SUV would get stuck. Same sort of thing. So we're detecting some information here. We're communicating. There's the Mars orbiter up there. So we're actually beam the information up to the Mars orbiter who beams it back down to JPL. Okay, so here we are moving. And this is probably faster than we would actually move. But this would be recklessly high speed for a driver. Look at all the little rocks and pebbles there. Just everybody's just terrified they're going to stick in a wheel somehow and jam the wheel up, so you have to drag it. We've drug wheels before, all kinds of things. Notice that it's mountainous in Mars. Obviously, some of those sand dunes there we could get stuck in. That's how we lost Spirit. We just got stuck in a sand dune. There was something really interesting we wanted to look at. There's kind of some sort of little dust storm over there. We don't move very far, but we move a little bit towards something. As you go over rocks and stuff, you can see the rocker boogie system really is pretty ingenious in terms of not able to get stuck very easily, really able to get through lots of stuff. All right, there it is, spelling out JPL in the sand. All right. So the scientists have daily arguments about where to go. Like someone says, I'm going to go look at that mountain. Someone says, hey, that's a long ways away. It'll take us 3 days to get there. And I don't think the science is worth it. All right. Someone says, well, yeah, but look at that. We've got a rock shelf that's barren. We don't have to dust it off. We have no way of, there's no dust cloth or anything. So they have to count on when they see opportunities like that and say, well, this is a chance to go really look at the bedrock. Okay. All right. We'll go do that. Somebody have a question? So this makes it look like they just drive right over there, but in actuality, they're just driving in short sections. We drive a few feet, make sure that nothing's broken, then we drive a few more feet. So it's really a sort of a tedious process. I've talked to some of the rover drivers, and they're just incredibly patient people, thank God, and very, very cautious. So this looks like sediment. So it kind of looks like layers of lasagna on some of these rocks like this. Look at other ones. So what they're doing is zapping it with a laser, and then the camera can actually pick up the radiation, and other devices there on the rover can pick up the radiation from the zapping. And that's what they want to measure, because they can get composition of the rocks based on that. Okay, now we found something close enough to a rock we want to drill something. Here they are taking the drill out. John, you asked how it goes. One thing that limits the effective life of the rovers also is how many drills they can carry. Once we drill something, we get Martian soil into the drill bit, we have to throw it away, and we get another drill bit. We don't have any way to clean the drill bit. Now, that clock in the center says that happens about 100 times that slow. Just for the purpose of this video. All right. We've got a core sample now stuck into the drill bit. All right. And so we're going to position the arm. Right, and then we're going to take it back to the rover, right? And what we want to do is analyze the soil. So it's a little lab. They actually called this the Mars lab. It's actually a little lab inside the rover here. So I'm going to drop the soil that I collected, into the lab. And here I've got spectrometers and all kinds of other scientific equipment. I can spread the dirt out. I can look at it with various equipment, lasers, other things, and try to understand the composition of the soil better. And when they did all this, they were able to find evidence that proved conclusively that water was on the surface of Mars at one point in time. We know that there's Mars. We haven't found any organisms yet, but we do know that there are organisms that are capable, and they make projections of what, as you saw, what Mars might have looked like 3.8 million years ago. And certainly it looks like it was capable of supporting life of a variety of sorts back then. All right, so off to find another rock here. Think about the highest mountain on Mars being 3 times as high as Mount Everest. It's just amazing, and it's a mountain that blew up. It's actually a dormant volcano, so that must have been there. Very interesting. Any questions before we go on a little bit?
How many miles then do they average on a daytime if they move so slow? I mean,
Probably half a mile.
oh, okay.
If that. Some days they'll only move a few feet because they're exploring rocks, you know, they got to. But if they were going to go transfer to something like that, I want to go over and look at the foothills over there. That might be a couple miles away, so it might take 4 or 5 days to get.
Rick, are you going to talk about the drone that's on there?
Yep, I will.
Thank you.
So actually, this is actually the old one, the Curiosity. Let's move and talk about Perseverance for a little bit. So Perseverance, a little bigger, much more sophisticated equipment. Of course, now we can only afford to launch one of these about every 10 years. So we really have to pack a lot of science into it. We're reusing a lot of things that we've done before. So you can see it's still got a drill. The drill works a little differently, a little more efficiently, things that we learned about drilling in Martian soil. It's got a mass cam. It's got a little bit more sophisticated, kind of like, you know, your iPhone has the newer model has a little bit better camera than the last one. Some other types of equipment, et cetera. We're going to show you some equipment in just a second here. And they're stepping up the mission a little bit. So now we're trying to really determine, was it habitable, okay? Or could it be habitable now? So we're moving towards, can we put humans on Mars? Okay, so the question is, how could we make Mars habitable? So a couple different things. Think about, we need, what do we need to put a permanent colony on Mars? Well, we need to be able to build structures, and we need to be able to create oxygen. And so there's a little device on here that we're going to look at that creates oxygen from carbon dioxide. So we think we could do that in grand scale to provide oxygen for humans. And then we're looking at the soil to see, could we use the soil to compact it, make it into bricks, and build our Martian habitats out of the soil that's on Mars. And I've seen some designs for some robots that actually just scoop up on Mars, make it into a brick, and then stack the bricks on top of each other and build buildings that way. So a building completely built by a robot or a set of robots. Really fascinating stuff. We're also looking for biosignatures. That's evidence that life was there and what type of life it might have been. One of the interesting things is we're caching samples. So caching means, you know, to leave something where somebody else can find something. You saw that we took the soil from the drill and we put it in the little onboard lab and we analyzed a little bit. Well, our labs back here are much more capable of doing, more sophisticated analysis, but there's no way of getting the soil back here where our labs on Earth can look at it. This, the Perseverance is actually collecting soil, putting it in little tubes and dropping the tubes on the surface of Mars with the idea that in 10 years, we're going to go back up there with a more sophisticated craft that can pick up those tubes and bring them back to Earth. So really ambitious here. And just generally preparing for human habitation, which we think, might happen 2050, maybe 2060. But towards the end of, certainly in our kids' lifetime, anyway.
So Rick, how are humans going to exist on Mars without water?
So that's one of the ideas in terms of converting the carbon dioxide. Can we take enough hydrogen? Can we create hydrogen? Can we find enough hydrogen that we could create water there as well? So that would be another thing that we have to
I don't understand. How do you find water, hydrogen?
You'd have to take hydrogen, or you'd have to find enough of it in the atmosphere.
All right.
Or you'd have to find springs that might be below surface. So some scientists will argue that there's actually water below the surface of Mars. We just haven't figured out how to drill down far enough to get a hold of it.
One thing, though, that I think in the popular imagination people don't understand is you're not going to terraform Mars. The reason it doesn't have an atmosphere is because it doesn't have a magnetosphere. It had an atmosphere and it blew away when the core froze. So you can't terraform Mars. You could make a bubble. So, I mean, colonizing Mars is about the same as colonizing the moon. I mean, you could bring stuff from Earth to the moon much more easily than bring stuff to Mars. So anything about taking water and taking whatever, would be much easier to do on the moon. And you can never make Mars habitable. You can put a habitat on Mars, but that's a very different thing from making Mars habitable.
Right. It's like making the Antarctica habitable. You're not going to walk outside in your shirt sleeves. What you can do is build a building and make sure you stay inside of it, and you might be okay for a while. Same thing on Mars.
Yeah, only the advantage is that on Antarctica, we have the atmosphere, we have the water, we have the gravity that's the right amount, so our muscles don't get all screwed up. So there are some big advantages to colonizing Antarctica or the Sahara or lots of other places before we colonize Mars.
Yeah, you can argue with the scientists about that. Here's just a little bit of an overview of some of the equipment on the new Perseverance rover here. And here's the graphic. So let's show you what some of this cool stuff can do.
Mars is the closest place that we can reach with robotic exploration that we think had a really good chance of having ancient life.
The Perseverance rover will land at a location called Jezero Crater. Jezero Crater is a very interesting place. It's a crater that once held a lake.
There are a lot of craters on the surface of Mars that could have once hosted ancient lakes, but not every crater that we think had a lake actually preserves evidence that that lake was there.
It had an inflow channel and it had an outflow channel. That means it was filled. The crater was filled with water.
In Jezero, we have probably one of the most beautifully preserved delta deposits on Mars in that crater.
This is a wonderful place to live for microorganisms. And it is also a wonderful place for those microorganisms to be preserved so that we can find them now so many billions of years later.
There is no other place on Mars that has the unique combination of a lake setting, a beautifully preserved delta, and the diverse mineralogy that we have in Jezero Crater. So it's truly a special landing site.
The major goal of the Perseverance mission is to investigate astrobiology on Mars, and in particular, to address the question of whether life ever existed on Mars. The Perseverance rover starts with a design that's very similar to Curiosity, but we've added to it a whole new set of science instruments. And these science instruments were purposefully selected to help us in the search for biosignatures.
We're going to be taking microphones with us. For the first time, we're going to have that human sense on another planet.
Perseverance carries with her a grand experiment in spacefaring technology, a helicopter, the name of which is now Ingenuity.
One of the major upgrades that Perseverance has from Curiosity is that it's able to self-drive for a distance of up to 200 meters per day. As the rover is driving, it's literally building the map of the road it's driving on Mars.
Scientists for years have told us that to really unlock the secrets of Mars, we have to bring samples from Mars back to Earth.
So what Mars 2020 is going to do is to drill samples, put them in small tubes. We're going to seal it in its own individual tube. We set them on the surface to provide a target for the second two missions, which hopefully will get in development in the next several years and could potentially get the samples back to Earth by 2031.
Perseverance is a very, very profound first step in both our understanding of our place in the universe and a stepping stone towards human exploration on Mars.
So a couple cool things there. You saw a little bit about the drone helicopter that they have, so we can fly that around. That's giving us some interesting, will give us some interesting views of the rover. We can also explore parts of the surface of Mars that we don't have time to drive to. We can fly the helicopter over there and back. You saw some of the cool equipment that we have, more cameras. One of the interesting things is that when you're watching the landing, watching is a weird comment because you're really just getting data about the landing. And the data that you get about the landing just says that the equipment thinks it's working properly. You get some information about things like height and you can see various software packages kick on and things like that, which gives you confidence that things are proceeding the way you want. When landings don't go well, what happens is all of a sudden you just get radio silence. And you know that something crashed and you quite often have no idea what exactly went wrong. And we've had a few crashes on Mars with a few things as well. This, for the first time, we've got pictures. So we actually have pictures that they've already sent back of what the landing looked like from different perspectives. We can kind of see that. We can kind of compare notes there versus notes here. One of the biggest problems is, we don't work in third gravity any place here. So we don't, theoretically, we know how the equations work for things like landings and stuff, but you don't know the details of how something's working. And so we're going to show a video in a second that kind of gives you some of the scariness of that. But first time now we've got pictures coming back from Mars of some of the actual equipment. And as you heard mentioned there, for the first time, we've got audio. And they've actually, it's been up on Mars now for about 3-4 weeks. Perseverance has been, and we actually have our first audio signatures back. And I thought about playing some of them here, but they're not very interesting. It's like putting a camera outside your house. What you hear is you hear the hum of the equipment on Perseverance, and you hear the Martian wind at times, and they can actually isolate those with soundboards and just hear the wind. So that doesn't sound very amazing, but to actually hear wind from the surface of Mars makes geeks like us really, really, really excited. Any questions about any of the equipment?
I have a question about the Earth. I've been to Sedona in New Mexico and got all red dust all over me in Sedona. Is the soil on Mars similar, or is there an identical place on Earth where it's the same?
Yeah, probably very similar to the desert Southwest. Probably more dust. And then the third gravity kind of means that things don't get way down as fast. So the dust will float in the air a little bit more. So you see those sort of dust sandstorms a lot. And then of course there's no vegetation or anything any place.
And that redness is caused by iron content?
There's iron content there. We think there's iron core. There's other minerals there in the earth. But yeah, there's the dust is partially sand, like a silica type of material, and partially iron and rust type things. Okay, John, you were asking about landing, and I thought maybe you'd like to see a little about how we landed the rover. It turns out that's the most complicated thing. It's pretty easy to launch the rover from Earth. It's pretty easy to navigate to Mars. Recognize that we want to set the rover down in a particularly safe place next to some really interesting geology. So we have to be kind of precise about where we enter the Martian atmosphere, with the idea, because we're not going to be able to steer around once we get inside. But I've got a little video here that shows how they actually got the rover safely down onto the surface of Mars. So let's show that.
Nothing can be taken for granted when you get to Mars. There's a lot of things we just don't know.
Space always has a way of throwing us curveballs and surprising us.
I mean, until we get the data that says we're on the ground safely, I'm going to be worried that we're not going to make it.
Entry, descent, and landing is often referred to as the 7 minutes of terror, because it takes about 7 minutes to get from the top of the atmosphere of Mars to the ground safely.
The spacecraft has to do all of this by itself.
There are many things that have to go right to get Perseverance onto the ground safely.
There's a lot counting on this. This is the first leg of our sample return relay race. There's a lot of work on the line.
Starting about 10 minutes before atmospheric entry, we get rid of really the spacecraft part of the rover that's been supporting us.
We come screaming in to the Martian atmosphere at 12 to 13,000 miles per hour.
And the heat shield is what dissipates all that initial energy through friction.
The vehicle will continue actually flying itself through the atmosphere. It's sort of like a transforming vehicle that went from a spacecraft, and now it's kind of like an aircraft actively guiding itself.
When we're going slow enough, we deploy a parachute.
It's the biggest supersonic parachute we've ever sent to another planet. It's critical for slowing down the vehicle.
Perseverance's entry, descent, and landing borrows heavily from that of Curiosity.
But fundamentally, Perseverance is a different rover. She's bigger, she has different instruments.
We've added a lot of smarts on the inside to make it more capable so that it can deal with the landing site that we've given it.
The science team identified Jezero Crater as basically an ancient lake bed and one of the most promising places to look for evidence of ancient microbial life and to collect samples for future return to Earth. The problem is it's a much more hazardous place to land.
When you look at Jezero, all you see is danger. How do we go to a site that we never thought was safe enough to go to before? So the heat shield, which has protected us all the way through entry, is no longer necessary. We need to get that off so that we can actually see the ground. And we can see the ground in a couple different ways.
Perseverance will be the first mission to use terrain relative navigation. So while it's descending on the parachute, it will actually be taking images of the surface of Mars and determining where to go based on what it sees. This is finally like landing with your eyes open. Having this new technology really allows Perseverance to land in much more challenging terrain than Curiosity or any previous Mars mission could. Amongst the rocks and the craters and the cliffs, these things are hazardous to the rover, but these are the things that are interesting to the scientists.
Once Perseverance has figured out where she is, we jettison the back shell and parachute and light up our rockets. Those rockets help us steer to a safe landing spot that's nearby.
That descent stage takes us all the way down to about 20 meters off the ground.
That's when we start the sky crane maneuver. Once the rover has hit the ground, the descent stage will cut loose from the rover and fly away to a safe distance. Surviving that 7 minutes is really just the beginning for Perseverance. Its job, right, being the first leg of sample return, to go look for those signs of past life on Mars. All that can't start until we get Perseverance safely to the ground. And then that's when the real mission begins.
Okay, so does that look crazy or what? it's funny, when I first saw the artist's conception of how they're going to land, I talked to the chief engineer on the project, and I said, you realize this is insane, right? And he said, well, yeah, you should see the ideas we rejected. This is the least insane of the ideas we came up with. So amazing, different than some of the others, this idea, the sky crane, et cetera, and be able to set something down gently, but you got something really, really heavy. And so you're trying to do that. But think of all the ways that they could go wrong. In my classes, I have them analyze that and start to come up with where are places that system could fail. And the one that we always keep coming back to is this parachute. Like they said, this is the biggest hypersonic, above the speed of sound parachute they've ever deployed. And the other problem is it's not like we can test it very effectively because we have to assume what's like in a third gravity, right? So how do you test a parachute? Turns out the way they test the parachute is they go into a giant wind tunnel and they inflate the parachute sideways with fans. And that way they can control the fans, they can control the speed, they can control what it sort of feels like at gravity. And the first time they used one of these parachutes to land a rover, they rented time. There's only one wind tunnel in the entire world that's big enough to do something of this magnitude in terms of parachutes. They built a parachute to be able to test exactly like the parachute they were going to use in the rover. They deployed the parachute inside the wind tunnel and it immediately shredded. And they went, wow, that wasn't good. Why did that happen? So, well, let's look at the film. And it turned out that in a cost-cutting move, they had not gotten high-speed cameras to watch the parachute deployment from all levels. And the cameras that they had, they couldn't see enough of what happened to have any understanding for why the parachute actually shredded. So now we have a failure in the one test we've done, and we have no idea why it failed, whether that failure would happen on Mars again. Okay, what do? Well, you go buy another parachute, you go rent more time in the wind tunnel, you buy the high-speed cameras this time and set them up, and you redeploy the parachute and test it again. So they did that the second time, and the second time the parachute works perfectly. Okay, now what do? You've got one failure under essentially the same situations, you've got a success. Is the failure real? Is it some weird situation, right? If this doesn't work, we're out this mission, right? It's 10 years before we do another one. Okay, so talk to the program manager. He said, okay, we're buying another parachute, get more time in the wind tunnel, we'll do it again. Third time, parachute opens perfectly. Okay. All right, what do? Time. Parachute opens perfectly. Now we're getting mad, right? One failure, 3 successes, right? On the 5th time, the parachute shreds again. And everybody's actually relieved because we can see why it shreds. It turns out it shreds because the cords on the bottom of the parachute got pushed through the parachute at supersonic speed, which is what managed to shred the parachute material. Then we do analysis and we figure out that actually couldn't happen on Mars because of the way the gravity works. It wouldn't work the same way. It's actually a phenomenology of the way we're testing it. And so the first failure we had that we couldn't replicate until the 5th failure was actually a failure that wouldn't happen. It didn't happen. But at least at that point, after spending a lot of money, we had some confidence that the parachute would work. So that's the life of an engineer, trying to figure out how things break and figure out what to do with it. So let me just conclude, and I'll take some questions if people have them, just by saying we're just starting to get some data back in here. We've already gotten the first pictures of the landing. We've already gotten some pictures of the site. We're just starting to do some of the science. We got Some of the cool things like auditory sounds, sounds from the Martian surface, etc. There's going to be some exciting things coming up. You're going to hear a lot of cool science about this, and hopefully it sets us up for the next generation talking about habitation on Mars. So with that, I'd be happy to take any other questions that anybody has.
Well, the sky crane, was that also the technique that was used on the predecessor mission? I mean, I know the scale, like when it gets much bigger and heavier, it's a lot harder, but did they do the same sky crane, lower it down and fly away on the previous mission?
Yeah, Opportunity used the sky crane also.
Right. But they had to scale it up by a huge factor because of the heavier vehicle. Right?
That's right. And that's what they're worried about was the bridle. You can see there's 3 bridles. And that means you have to have three pyrotechnic devices that cut the bridles all at the same time, so you don't jerk it over on its side or something like that. So a little bit of trickiness there, but same idea. Opportunity had one big strong bridle that dropped it down, so we only had one cut.
Oh, okay. Yeah, so so you didn't have to worry about that synchronization problem. Yeah.
So Rick, on the samples, the core samples they're leaving around the Martian surface, I presume you map those, and obviously nobody's going to come by it, pick it up, or animal take it away. But
we hope no little green men are going to steal
the wind. But the wind.
You do have storms, and I'm just wondering if the storms were to blow it around or something, you have trouble searching and finding them.
Yeah, they're heavy enough. We won't worry about them blowing them someplace, but what we could do is cover them with dust. The storms could do that. So think about, we're talking 10 years from now, we go back to get them. So if you notice, they're kind of a metallic, so it should be easy to find them with sensitive equipment. The harder thing is the 2 hard parts is how do you pick them up in some way and put them in a rocket to take back to Earth, and then how do you take enough propellant up there with you so the rocket can go back, right? It's fairly complicated. Apollo kind of made it look easy, right? But it's actually really super hard to take enough propellant up with you that then you can launch off the surface. The third gravity helps a little bit, but I'll tell you that the scientists are completely geeked out about having samples. When Apollo brought back moon rocks, they took them to a lab there at Caltech. We were the lab that got to do the first analysis on the moon rocks. And so we've already got geologists at Caltech who are salivating, for 10 years from now, be able to have these core samples that they'll be able to play with.
So Rick, do they still have lectures at Caltech that the public can tune into?
Yeah, absolutely. If you go to caltech.edu, you'll see all kinds of lectures. You can even sign up for like a little mailing list, and they'll send you about them. But there are a lot of different public lectures, and a lot of times the JPLers come up and lectures. I'm privileged enough. I've got when we're in session up there, which we're not right now, but when we're in session, I can actually coax a lot of the JPLers to come over and talk to my classes, and they always find it fascinating. And these guys are fun, interesting people with really interesting hobbies, just on top of just being absolutely brilliant sort of people. So,
so 60 years ago, after Sputnik, we had a big interest in science, and so for extra credit in my 10th grade science class, we could go to Caltech lectures and write up, and trying to figure out how to write up all the information about lasers and robotics and RNA and DNA, which was sort of the cutting edge stuff at the time, was an interesting aspect of my 10th grade science education.
Oh, that's great. Yeah, that's the kind of stuff that got us interested in STEM early on, got my kids interested in STEM.
Yeah.
That kind of fun stuff. And both JPL and Caltech are just kind of a playground for us science geeks. For example, we've got a robot that looks a little like an ostrich that just walks around on campus and delivers things.
I've seen that.
I'll talk to you guys about that sometime. That's just fascinating sign of that. And it's actually being adapted now. What they want to do is make it into a prosthetic device for people that have lost a limb or lost 2 legs, and people be able to walk around like that. That's their eventual goal. So.
Rick, do we have any idea of how much the area is that we've explored of Mars?
Oh, tiny part.
That's what I was thinking.
Rick, I have
1/100th of 1%.
Rick.
Yeah.
I wonder if this is probably all classified information, but there must be people that are sitting around thinking, what are the military uses of all this research? What are the geopolitical implications? Foreign policy implications. Is that part of NASA, or is that done by some other group, or is it done at all, as far as you know?
NASA gets some research from research money from the military to do some things. It mostly is technologies. So what the military is interested in is like energy generation with the radioisotope, or the way some of the cameras work. Could that be used in the battlefield, et cetera? There's not too much crossover on the program, so there's not a lot of direct interest. We do work with people like European Space Agency on some of these planetary stuff. So the ESA is actually the ones really interested in in dropping the samples and picking them up, what's called the sample return portion of the mission. And there's some military interest up there, but they tend to be on other kinds of programs. There's not as much direct interest.
National Security Space is more like Aerospace Corporation rather than JPL.
Yeah.
Quick question, Rick. What's the long-term disposition of all this equipment and detritus that we're depositing on Mars?
We're Americans. When the cars don't work, we just leave them up on blocks in the front.
We should be sending our garbage up there then, right? Parachutes and, well, the equipment, will it rot or decay in any sense in that environment?
Yeah, not very quickly. It doesn't have the right kind of atmosphere. So eventually, probably yes. But stuff like all the metals and stuff that are in the things, it's not gonna do it. In fact, one of the biggest concerns when we're doing things like drilling for samples, looking at that, we're very concerned that we're contaminating the very field that we're trying to do. So if I had microbes on the side of the rover and I landed and then I looked down, picked up a soil sample and it had a microbe in it, I've just compromised myself. So we're a little concerned that there's actually a whole office that looks at are we polluting is maybe a simplistic way of doing. Are we creating problems on Mars from the perspective of science, or just from the perspective of being good ethical citizens?
And to me, that's a massive reason not to ever send a human to Mars until we have definitively proven there is no life or trace of life on Mars. Because once we put humans there, there will be tons of traces.
Yeah. So
good point.
It's kind of like dropping a coffee cup in Kansas, though. The Mars is so, you saw the surface area of Mars is the surface area of all the continents. So a couple of dead cars is probably not going to be too big a deal.
Well, that was once thought about our space, atmosphere here and satellite detritus and stuff. I mean, I'm surprised that we can continue to put things into the orbit around Earth without running into space trash.
There's a whole team of folks. One of my friends at Aerospace Corporation is in charge of the entire team that just tracks all that space junk, and they are constantly having to warn spacecraft to get out of the way of somebody else's junk. That turns out to be a huge problem, Frank.
And the problem also is that you can only track objects down to a certain size. But at orbital velocities, really small objects can do really huge damage. That's a very, and especially with like SpaceX now launching things like crazy, launching, I mean, in the entire history of the space program, we launched, hundreds-ish of satellites for decades. And now they're talking about launching thousands. So it's a whole different world. It's going to be a real adventure to control that.
So millions and millions years ago, there's got to be oxygen because there's water, right? There are craters. And the fact that Mars is red because iron oxidized. The only way iron can oxidize is the presence of oxygen. So
That's right.
this
So-
whole situation might return in another.
No, it can't return. No, it's not reversible because it used to have a magnetosphere. The reason Earth has an atmosphere is because it has a magnetosphere. The magnetosphere protects the Earth from the solar wind. If the magnetic field were to go away, which it did on Mars, because Mars is smaller, so it cooled faster, so the molten core is now solid. It no longer has a molten core. It no longer has a magnetic field. Once the magnetic field is gone, the solar wind, these ionizing particles, strip the atmosphere. And that's why there's hardly any atmosphere left. It got peeled away by the relentless pressure of the solar wind. So it's not coming back. It got blown out of the solar
Can it go
system.
forward then? If it's not going back, can it go
No.
forward?
It got blown out of the solar system. It got peeled off of the surface of Mars, and it got blown out of the solar system. The solar wind blows in one direction, out
So
from the
one of
sun.
these days, the Earth might get blown away then.
Well, yeah. After our core freezes, after our core is no longer molten, the same thing will happen to Earth. Once there's no longer a magnetic field, Earth's atmosphere will also get peeled off.
Luckily, none of us will be around to see any of that.
So Rick, we have to sign off in a minute or two.
It's 10 o'clock, yeah.
Okay, thanks, everybody.
Thank you. That
Thank
was
you.
interesting, Rick. Very, very.
Very good.
Thank you all.
Thank you.
Thanks a lot, Rick.